In this video, I'll explain one of the meaning of entropy. So what is entropy? Entropy is this. Let's say X is generated from a distribution P, X. The entropy of random variable X is equal to minus sum over X for all possible outcome Px times log Px. This is the definition of entropy. So this is equal to expectation with respect to x comes from distribution Px minus log Px. So this is the definition of entropy. And maybe you heard that entropy represents the amount of information the random variable x has. So I will explain why entropy can indicate the amount of information. Let's assume this scenario. There is one machine and there is another machine. There is machine A and machine B. And machine A have to send some information to machine B. So what kind of information? Let's assume there are n number of random variable, x1, x2, that are up to xn, and each xi is IID random variable comes from or following the distribution Px. Okay, so at each time, time 1, time 2, we randomly generate a value from x1 to xn, and we have to send some information, or we have to send all the information to machine B. Right? We have to. Let's consider this scenario. And to make the problem more simple, let's assume all xi value is either 0 or 1. Right. Then the question is this. How many bits do we need to send the random outcome to machine B? Okay, so this is our main question. One naive algorithm is just simple coding. So just write down the outcomes. So 0, 1, 0, 0, 1, 0, 1, something. The real outcome. We just send this real outcome. Then we need n bits to machine B. We need n bits to send all information to machine B for each time, of course. But this is not the optimal way. There are many other methods that can save the number of bits. We can compress the information. Okay, so how can we compress the information? Let's think about the meaning of log probability. So what is the log probability of the random realization from x1 to xn? So since we assume that each random variable is IID random variable following the distribution P, so this is equal to sum of minus log p x I. And again, let's make problem simple. Let's think n go to infinity. Then what will happen? Essentially, from the row of large number, this is almost same with my n times expectation with respect to random variable x comes from the distribution px minus log px from the log of large number. And from the definition of entropy, this is equal to n times entropy of random variable x. Right? So from this, we can define an epsilon typical set denoted by a epsilon n. So this is epsilon typical set precisely set of random sequence xn through xn that satisfy log p x1 to xn plus n entropy of x is less than or equal to epsilon. Right. So from the concentration inequality, from the law of large number, we know that most of random outcomes belong to epsilon typical set with any tiny small epsilon value. But we also know that the probability of x1 to xn is equal to exponential minus nhx. Of course, there is some plus minus epsilon there. When x1 through xn belong to epsilon typical set. From this, we know that the cardinality of epsilon typical set is roughly exponential n to the hx. Okay, so we almost there. So from this property, we can think a very interesting compression technique. We can design a codebook for typical set. We just use n times h entropy amount of bit. With this amount of bit, we can still represent all possible elements belong to the epsilon typical set, because the cardinality of epsilon typical set was exponential nhp. So we just need this amount of bit to represent all elements belong to epsilon typical set, except all zero chord word. So when you look at the first n times entropy of p bit, and when there is at least one non-zero element, we can notice that the chord word represents one of epsilon typical set element, and we can successfully decode the real original message. But when the first n entropy of p bits are all 0, then we know that the code word will not belong to Epsilon Typical Set. In that case, we use n bits to express all the remaining other random realizations. Okay? So on average, because almost every element, almost every outcomes will belong to Epsilon Typical Set, on average, we just need n times HP bit, n times entropy of p bit to represent the random outcomes. These n bits will be negligible because the event, the random realization, does not belong to Epsilon Typical Set, will be almost never happen. Okay? So that's why entropy kind of amount of information we have to use to send the old message to other machine. Okay, so this was very naive idea. Essentially, when you have a random realization from x1 to xn, and if you know the true property for this random sequence, there are many coding methods that just use minus log p x1 to xn bit to represent this x1 to xn sequence. So for instance, Huffman code, it uses minus log probability bit to present a random sequence. Then essentially we just need expectation with respect to x from the distribution p minus log p of x amount of bit to represent your random values. So this entropy is the amount of information of your random variable.